hello everyone. I'm Michał Taraska. I'm a Standardization Manager in Connectivity in IDEMIA. I joined recently, like 3 months ago, so still new there. But before that, I was quite deeply involved in 4G and 5G stuff for a few years. So I would like to share some of my knowledge with you. And I think we will try to find the answer to the questions we all have in the bottom of our hearts. So do we need the foil hat? And if yes, how thick it should be. So let's start with the agenda of what I have prepared. I have divided this small presentation in 4 parts. And we'll start with briefly history of 5G and what G exactly is and what generation we have before. Then we'll go to what is new and what is old. So what we'll use from 4G and what new features we'll introduce in 5G to make this technology happen. Then we'll talk a bit about interoperability of these two systems. So if showing of 5G will just shut down the 4G network, how this will play out. And at the end, we will look a bit on the business opportunities and we'll ask the question why we actually need 5G and how we can use it. So let's jump to the first topic. So short history of the telecommunication technology. So if we are talking about the modern technologies of telecommunications, because if we would like to stick to the definitions, then we don't need any kind of electricity to make a telecommunication happen. So if we are not talking about modern telecommunication, then the first telecommunication is like smoke signals because they are meeting the definitions. But when it comes to the modern times, the first G appears around 1983. And during time, more and more requirements were added to the technology and another generations have been formed. And who is adding these requirements? The requirements are added by organizations named 3GPP. And the 3GPP basically is researching and thinking how we can improve what we have. They are forming some requirements, and then companies and network operators and people, researchers from over the world are trying to find the way to meet such requirements. It's not always such easy because, in example, when the 4G was proposed, the deadline and the release was planned for 2028. Sorry, 2008, not 28, not yet there. So, and the official release, if we look in the documentation, is 2008. But in reality, not all requirements have been met there. And if you will look deeper, actually what we got in 2008 was 3.95G, because we only have like 95% of requirements fulfilled. And real 4G was released in 2011, but because world already used 4G for 3 years, they need to find a new name for that. So they come with the LTE Advanced, and that was the initial plan for 4G. And we see that happening right now with 5G, because 5G already for 2023, so for the end of the next year, already is planned the release of 5G Advanced. So this Advanced means that that's all things that didn't meet the deadline of the initial 5G and was just moved to another release. But what requirements and what is the definition of 5G? So there is no formal definition of 5G. You can't find the document where there will be a plain text with the 5G that, and that. Rather, we have like group of requirements, and we can distinguish some areas for these groups. And usually they're shown as a triangle like this on the slide. And there are 3 main areas connected to different, let's say, industries and different needs that will use 5G. So MMTC is all about the IoT devices. This is the area of requirements that is connected to battery life, to the density of the network, of the less complexity that we need to introduce to IoT device to make them work as they are intended. So in this area, we'll see all these requirements. I will show a bit more details in the few slides. The top area, the EMBB, is all about improving what we already have in 4G. So it's about getting higher throughput, getting lower latency, getting more spectral efficiency. So spectral efficiency means that with the same part of the bandwidth, we can work with more devices at the same time. So it's all about more, more, and more. And the third group is all about the serviceability and reliability. So we want to have a system that will allow our devices to be connected for almost whole life cycle. We want to have the low packet error, we have to have low latency, we want to have the full coverage. And this is because 5G is aiming for a lot of industries that depends on the fact that the machinery will be online for the whole time. Like, we can expect to have autonomous cars that will be lagging or will lose the connectivity on the middle of the road, because this can lead to the disaster. So this is this group of requirements. And if we will go a bit deeper into the details, there are like 8 main requirements for initial 5G. There is much more, but that was like the key point when the 5G was formed. And I will not go through all of them. So I think the most selling point of 5G are the biggest throughput. So initial plan was to get 10 gigabytes per second throughput. This is a bit of a lie, because currently the high bands allow us to achieve around 1 to 3 gigabytes per second. And those of you that are familiar with 4G may know that in 4G we already achieved 1 gigabyte per second, but in 4G it was done only via carrier aggregation, so using more cells than one for one UE. And in 5G we are achieving this speed of 1 to 3 gigabytes using only one cell. And with carrier aggregation, then we can achieve 10 gigabytes. And the second biggest selling point, and the most, in my opinion, most important feature of 5G is this low latency, the going under 5 milliseconds. Again, if you will open the internet and some white papers, usually they try to say that this latency will be 1 millisecond. This is also not true, because it depends on the band we'll use. But 5 milliseconds already allow us to do real lifetime operations during the machinery. So this is enough to provide the continuity of usage and putting it frankly not lagging when we are using our device. And then we have like a bunch of requirements connected to the density of the fact that with 5G we are planning to add more and more and more devices to the network. So we need to have a capacity and coverage for that. And of course, like I think every modern technology, go green requirements. So reduction in usage of energy, the battery life cycle for IoT. So some IoT, especially these small devices like smoke detectors, should have like battery life that will allow them to live for 10 years. You just plant it somewhere and leave it for 10 years, and then after 10 years, someone comes, replace the battery, and it works again and again and again. And that is the brief history and brief background to start to talk about more advanced stuff. So now we have, let's say, a brief definition of 5G in our heads. And now we can talk about more technical stuff. And this slide will be more scary. So this presents the key features that have been introduced for 5G to work, and key features that have been only changed. And again, if someone have a deep background in 4G, this slide may look a little odd, because MIMO and beam management is not something new. It's something that exists in 4G, but it was an optional feature in 4G. And they are mandatory key features in 5G, because you can't have 5G without beam management and massive MIMO. And that's why they are marked as new on this slide. I will also not go through all of these bubbles through all my presentation, because that would require like a whole day of talking. So I'll just pick some of them. I will skip for sure the SDA pay layer, because it would be required to show you the whole architectural stack of for 5G and LTE and go through that. So I think we do not have time for that. LDPC and polar coding are very deep topics about parity checking. So I also think this presentation is not fit to show them, because we would have to go through analyzing the density of the matrices and go to a lot of math, so not today. And I will also skip the massive MIMO per se, because massive MIMO, as I said, is not something exactly new. It's just using much more antennas to MIMO. For those of you that do not know what MIMO is, MIMO means multiple input, multiple output. So we are sending our signals from, let's say in the most classic example, from a lot of antennas, or 10 antennas to, and we are receiving the input in also with 10 antennas. And thanks to MIMO, we can increase throughput, or we can send the same signal 10 times. So we can increase the probability that the signal will reach the target. So that is the MIMO in very short. And we'll focus more on millimeter waves, beam management, and multiple numerology. And I will start with numerology because numerology is also connected to the subframe structure, which is only slightly modified from the 4G. So what is a numerology? For those of you that are more familiar with pop culture, not with the 4G, you can hear that Hermione from Harry Potter was in the numerology classes, but this is not this numerology we'll talk about, probably because this is also magic. So what is numerology? In 4G, we only use one numerology. That's why this topic was never bring up. Because to understand the numerology, we need to understand how the signal is sent in the telecommunication technology. So in telecommunication, we operate on two resources. We are operating on time and we are operating on frequencies. And the basic of sending signal is that we are generating some wave during time, and we are generating actually parallel waves that are shifted in frequency, and we are sending them as a one signal, and via this wave, we are presenting the bits of data we want to send. This is the basic. And in 4G, it was constant. We always used 180 kilohertz and 1 millisecond. That was the only frame structure that existed. And this 108 kilohertz was divided into 12 sections, 12 subcarriers. Why there was 12 subcarriers? Why each subcarrier was taking 15 kilohertz? It's because of physics. And to send such many waves in parallel and to avoid interferencing between each other, we have to use orthogonality. This is the property of the wave that means that the highest point of the parallel wave is in the minimum point of the second wave. So they do not interface with each other. So this is the basic behind what we do things like that. And in 5G, this was taken to another level. We introduced the possibility to change the spacing between these carriers. We still need orthogonal waves, but we can make the space wider. We can double this 15 kilohertz to 30 kilohertz. We can double 30 kilohertz to 60 kilohertz, and we always double the previous number, and you can see it on the table below. But we can't just do that without any cost. We can just double the spacing and that's all. Because if we will double the spacing, the wave generation will be a bit different from the hardware perspective. So we are paying with time. If we are doubling the space, we are halving the time. If we are doubling the doubling of the space, we are halving the halving of the time. So instead of generating these waves in 1 millisecond slot, we are dividing this slot to a half millisecond, 0.25 milliseconds, so on, so on, so on, so on. And if we want to go even deeper, each of these slots will be divided into 14 different symbols, and each of the symbols will generate the waveform. This waveform will be combined in one big wave, and this will be the data we would send. And for sure, you will raise the question why we do that, and why we change something that have worked for 4G. And this is because 5G going up in frequencies. And to paraphrase Uncle Ben from Spider-Man, with the great frequency comes the great Doppler effect. And the Doppler effect is something that you may be familiar with. And the Doppler effect is the physical interaction that damage the wave. And the base is that the higher is the frequency, the more intense the Doppler effect is. And the Doppler effect is also more intense the longer the wave is propagated, because it has more time to damage the wave. So the trick is, by increasing the space of subcarriers, as we said on the previous slide, we are cutting time in half. So we are giving Doppler effect less time to damage our waves. And if you will see on the range of the high bands have a very big range when it comes to frequencies, between 24 and 40 gigahertz. So we have like 16 gigahertz to operate on. For example, in the mid bands used in 4G, at the beginning of the 4G, we have only 1 per 6 gigahertz. So on the mid bands, increasing the spacing of the carrier, so increasing the usage of the bandwidth, was very costly because we have a very small bandwidth to operate with. On the 5G, it's not so costly because we have such wide bandwidth that we can pay the cost and decrease the time. This is the first reason why we introduced new numerology. Second reason is ECE, interfrequency carrier interference. It means that on the higher bands, when the waves are, I like the word, parallel to each other, then their interference with each other more. So by increasing the spacing between the waves, we are decreasing the ECE, so intercarrier interference. And this is the second reason why we are paying with time and increasing the bandwidth. And this is the, let's say, the fizzing reasoning. There is also the requirements reasoning, because we were talking about this low latency requirement. And what is latency? Latency is sending data to the target in the less time possible. And we are cutting time that we need to send the data. So this is the advantage for us. We are making the latency lower on the higher band. So one more question. Why then we just do not introduce one numerology with the higher spacing? This is because we'll use not only high bands, but also mid bands and low bands that have a different physical properties. And we want to keep the old methodology that we can just reuse in the mid band. And that's why this frame structure is only slightly modified in the 5G. Of course, there is one downgrade of this solution, because requirement of the 5G, the official requirements, and this is very important for us as IDEMIA, require all devices that operate in the network to support all numerology. We can't make a device that will only support numerology 2 and 3. All devices that want to use 5G need to support all numerology. So this put a more restraints and more, sometimes it will make hardware a bit more costly to prepare for that. There is also one additional info here. It's a bit deep, but treat it as something to tell your friends during the coffee. When you're sending the waves in any telecommunication, you are using something that is called diverse Fourier transformation. It's a mathematical equation to go from the frequency to the time domain. And to use this mathematical equation, you are picking the points on your radio frame for each subframe you are sending. And by increasing the spacing, we are generating less amount of subframes. So we need less amount of these points to make a Fourier transformation. And thanks to this, we can prepare the hardware that is less complicated for that on the higher bandwidth of 5G on the big cells. So this is also the reason to implement this higher numerology. Okay, I think that was the most deep slide we have. So no, it will be only better right now. Yeah. So, but now we are on the high bands. And the high bands, apart from 5G, have a very strict physics property. And the higher is the frequency, the shorter is the range of the signal we can send, and the weaker is the propagation, the weaker is the penetration of the wave. So if we want to send the signal from the high band, which are the main selling point of 5G, we need to use some tricks because normally when we are propagating the signal from the antenna, we are sending the same amount of energy in every direction. So this is the circle of energy. So the plus of this solution is that we do not care where is the UE, where is the equipment we are sending the data, because every direction we are sending the same amount of energy, so the coverage will be the same. But for the 5G, this solution would mean that we are sending a very short wave with a very short range with a very small amount of power everywhere, which is not optimal. So we are picking the point and we are targeting our wave to this point. So we are managing the beam. And thanks to that, because we are not propagating all the power, we can focus this power on one point, and thanks to this, make our wave a bit longer and a bit stronger. So we can penetrate more, for example, building walls or thicker trees to send our signal. And also we can reach UEs that are a bit further away from us that we would expect normally. To give you an example of the range we are talking about, in 4G, in the middle band, we have like range of few kilometers. On the low bands, we can cover hundreds of kilometers with one signal. On the high bands, the maximum output with beam management is around 1 mile. So it's 1.6 kilometers. So the downgrade in the range is very, very big. Of course, we have a lot of ways to send the beams to the UE. I will not cover that here. I will just say one more thing about that. That, of course, always there is always a price. So if we are sending the beam, if we are sending energy via the beam, not propelling all energy around, we need to find the UE we want to reach. So this is the point of discussion on the 5G forums. What will be the best possible solution to find the UE to send and how to manage its position, because usually the user equipment will move around. So we have to still know the position of the UE to send the data in the proper beam. And there is a lot of proposition, and probably this will be something very vendor specific and everybody will implement their own algorithms to do so. Like we have one of the first solution they're proposed. So we are just sending regularly random small signals like clockwise. And when UE will hear it, he will send some bits in the response. And then we have, okay, he is in this area. Now we will regularly send the information to this UE. And thanks to that, we'll keep the track of his position. So this is like the simple idea how we can manage the beam management. Why we are talking about beam forming and beam management? Beam management is the technology and idea behind that. Beam forming is the science behind how to do that. And this is a lot of matrix operations to just form the beam. That is the difference because these two works. And yeah, that are the basic, let's say, changes that at the beginning of forming 5G have been introduced. And now we should ask ourselves a question, how this will work with 4G. So we have currently a lot of 4G networks, but 5G is being prepared. And as you can see, the technology is a bit different in a lot of aspects. So how this can operate together? So in ideal world, it would look like that. The operator would modernize his network, would introduce 5G to the network, would inform all of his clients that, hey, we have 5G now, please throw away all of your devices that do not support 5G, buy devices that support 5G, and now we have 5G. That's like ideal world. But in normal world, there's plenty of requirements and plenty of ways and things that will determine where and how we will deploy the 5G. Because we can have the areas, like low urban areas, that we do not need 5G from the business perspective, because it will be not profitable to put a lot of money into new architecture and just to give 5G to 3 houses. There is a lot of things like business factor or spectrum factors that we'll cover in a few slides, that also shows that there is also always a decision. If we will use the spectrum for 4G or if we use the spectrum for 5G. So current, maybe not current, but the newest I could found situation on the world about 5G networks is like follow. So we have a very few blue areas, which mean standalone networks. This means that these are like pure 5G networks on the world, and they are mostly in USA, Asia countries, and Australia. Rest of the world is using non-standalone 5G. Non-standalone 5G means that we are adding a 5G to existing 4G network to get some of its benefits, but it's just like a tip of the iceberg. On this slide, you can also see this word 5G Extra One. 5G Extra One is an IDEMIA product. It's a SIM card that supports 5G, and those are the places that this solution have been used. And now we can talk a bit more about the standalone and non-standalone 5Gs. So this is what I just said to you, that standalone means that we have this dedicated 5G network and everything is working as it was intended to. But this is a costly solution because to introduce the 5G network, you have to modernize everything you already had from the 4G. So you have to like take everything down, put new antennas, stuff like that. So the usual way is to introduce the 5G plug, let's say, to existing 4G architecture and just add some 5G areas to this architecture. And we have a lot of non-standalone deployment possibilities on the world because you can add this plugin in different ways to your network. And the most popular one is option 3. And we will dive a bit deeper into option 3 because option 3 has 3 sub-options. So we have option 3, option 3A, and option 3X. And I may be wrong there, but I'm almost sure that option 3X is the most popular deployment in the non-standalone network in the world. And why is that? Because option 3X means that we have a core network of 4G, so EPC is from 4G. We have eNode B, so this is the radio station of 4G. And we are adding the gNode B, so the 5G radio station. And we are connecting the EPC with both eNode B and gNode B. And EPC, so the packet core, is dividing the traffic in the network between eNode B and gNode B. But in option 3X, we also give a possibility to gNode B, so to 5G antenna, to offload some of its traffic to the old 4G antenna. And that is the reason why we will use this deployment most often. Because thanks to this possibility of gNode B offloading the traffic to eNode B, EPC core can send more traffic to the 5G antenna. So it will prioritize 5G, and 5G will operate at the maximum capacity. It will send everything it could. So everyone in this network will benefit from the 5G. So the most customers will see that they have 5G in their phones, in their devices. And if EPC will send too much to the 5G station, then the 5G will just send it to the 4G antenna to cover this part of traffic. So that's why this is the most, let's say, selling idea, because the biggest amount of people will see that they are using 5G. And of course, they will see they are using 5G, but they will, maybe let's say a bit longer, but they will not benefit from everything that 5G can offer, because in the main requirements, the 5G architecture should be all clouded. We are not having the physical architecture beside the antenna for 5G network. And putting it in the cloud make all these, let's say, key features of 5G that I think will come in 3 or 4 slides from now to happen. And when we are plugging only our 5G antennas to existing 4G network, we are basically using other bands, like we can use high bands, and we can send more data. So we are just increasing the throughput and lowering the latency, but we are not talking about like networks-like things, like augmented reality, stuff like that. For this, we need to standalone network. Okay, so now we can go to this slide. You may ask, okay, so why will you not put the 4G network, 5G network, press all the buttons and start all of them? Because spectrum is a resource. It's not like you can just use whatever part of the spectrum you want. Actually, this is the situation in Poland right now. It's from March of this year. This is the spectrum division to all the operators that are operating in Poland. And this shows what part of the spectrum on the given band, given operator can use. And to get this spectrum, there are auctions held by the government, and operators are gathering there and they're buying the right to use this spectrum. So actually, as you can see, the amount of spectrum that the given operator can use is not so big. They have to operate really carefully on this spectrum. So when they have both 4G and 5G network, they have to decide how to split it between 5G and 4G. And if they see that, for example, in Łódź, there is not so many 5G capable devices, they will not use this very precious to them spectrum for 5G network, because it will not give them profit, basically. It's all about money. And that is also why the transition from 4G to 5G will be the same as it was from 3G to 4G. We'll have both of the networks ready to go, and we'll slowly shift from one network to other in the areas that we will see growth of the usage of the devices that use another network. So it's not like an instant process. It takes years to shift from one network to another. Actually, we are still using 3G in some areas, and you probably have experienced it yourself when you are going to some lake house or something like that, and you want to connect to the internet. You are losing your 5G LTE and you are going backward because modernization of the network on this particular area was not profitable. They just operators just stay with the 3G and that's it. And this is also the reason that this sentence, I think, is one of the most important sentences from this presentation, that there is no real 5G without 5G core. So this not standalone network, these plugins that will be used in the upcoming years are not real 5G. Real 5G comes only with standalone network and when we have a lot of 5G devices in the network, and we are using almost all of our spectrum to 5G, because then we'll be able to use all the features and all of the ideas behind the 5G. And now I think is the best time to talk about these ideas, these possibilities, where we actually want to use 5G. So there are some forecasts. They are from, I think, Ericsson from some time ago. And those are the statistics and forecasts of usage of data traffic per smartphone in gigabytes per month. And as you can see, they're rising. Every year they're rising, and not in the linear manner, but faster. Even in the year when the pandemic started, there is quite a bump in usage of the smartphone data because people were quarantined and they start to use their smartphone more. But I think the second graph is more interesting. This is the forecast of usage, not only the smartphone, but overall global mobile network data traffic. And this is not in the gigabytes, but an AB. So it's a million gigabytes. So these are millions of gigabytes usage. And as you can see, the forecast is that the purple space will slowly take over the orange space will take slowly from the purple space. So the dedicated 5G usage and the 5G spectrum will take from the purple one, which is used for both 4G, 5G, and little one of 3G. I see we are running out of time slowly, so I need to get faster. But we are at the end, actually. So the fundamental question for us, as we are sitting there, is, do we, as an individual customer, need 5G? And my answer would be not really. Because as an individual customers will only receive like more throughput and lower latency, so we can download the movie a bit faster. That is not the reason to pay more money to the operators for 5G. This is not the business case for the 5G. The 5G business cases are all in the industry. And that's why usually we will find out that 5G is called the industry revolution. Because low latency and high throughput allow us to do things that we were unable to do before in all kind of industry areas. We can think of infinite number of examples how we can utilize the real life operation of telecommunications. So let's talk a bit, let's find some examples. For example, smart factories. So we can have like group of dedicated drones that are observing or maintaining the machinery in the given factory. If the drones are still connected to the network and they have 100% availability, then they can do that. We can have driverless transportation, like train transportation, because railroads are the easiest way to connect to the 5G. You are just putting the 5G antennas along the train rails and sending the train without any humans on it. We can go with the AR gaming. A few years ago, there was this Pokemon Go that go to the world, and it had the augmented reality feature, but no one was using it because it was overheating your phone and draining battery capacity. But with the real 5G, we can like reuse it and even improve it. We can have augmented reality shopping, which is also the idea that is starting to be already implemented in the world. So it's like you are going to buy your shoes, you are trying your shoes, but you do not like the color. So instead of going to the shelf and looking for another color or another design of the shoes, you can pick your smartphone, scan it, and just check the colors, how they will look on your feed during the augmented reality. And that is the reason to buy and invest in 5G, not the fast internet in your phone. This is the industry technology. And because of that, there is a concept of network slicing. And this is the almost the last slide. So because we have a lot of industries that will want to use 5G, they will have different needs. And that is the way, that is the reason why the 5G architecture should be moved to cloud. Because if we have different industries with different needs, because for example, these drones I was mentioning will need low latency, but not a high throughput. But the gaming will need a higher throughput, but maybe latency do not need to be under 1 millisecond or 2 milliseconds. So by slicing the network, that's from why the name comes, the slicing, network slicing, we can logically divide in our architecture the operations that we can do on the set of data or set of information, and implement like quality of service for the given industry to provide them with exactly what they need. And the industries will not buy 5G, but they will buy the 5G slices that are defined in 3GPP for the given industry. So they, for example, will be able to buy 5G for massive machine type communication. And this will be the part of this cloudy architecture that will implement set of rules that will allow this certain industry to work at its max efficiency. And of course, 3GPP had to define some of the areas, because without this definition, every industry would like to buy its own slice with all set of rules. So implementation would be impossible for people like us. So there had to be some constraints. But I'm almost sure that in the next version of 5G, more and more slices will be introduced, and probably there will be the way for a big companies to request a very specific set of rules to be implemented for their given solution, just for enough money to pay. And that is something that I would like to close the presentation with. So with this industry focused way. So I thank you very much for your attention. We probably don't have much time for Q&A because we are already over the time, but you can also always catch me during the breaks, or try to catch me on Teams or something. I'm there, and ask me questions. Maybe I will be able to answer, maybe not. It depends on the question. So thank you very much, guys, and see you on the coffee break.